Okay, wait a minute. All right, so Sierra, we just got started. We just got done going over the test, and then figure out how people will get some points back, and so on. And then we had some talks about homeworks and so on. And right now we're in the middle of a discussion with Haley, who didn't get her homework completely done because of a pumpkin-related pie. Were they burned? Were they burned? They were burned. Okay. Before we start, tell me your feelings on pumpkin-related dishes. Pumpkin pie, pumpkin bars, other such things.
I've just bought like all of that. And pumpkin spice cake and pumpkin coffee and pumpkin
See,
okay. pumpkin donuts.
My quantitative reasoning class had some problems that involved pumpkins, and they freaked out about it. They're like, who eats pumpkin? And they're like, pumpkin pie is terrible, and pumpkin bars are terrible, and it's like a punishment to have to eat this at Thanksgiving. And I'm like, what the heck are you talking about?
She turns into a pumpkin in the fall.
And Andrew, what's your feeling on pumpkin?
I love pumpkin pie.
Pumpkin's awesome.
I eat one by myself every year.
Every year. My kids are obsessed with pumpkin.
Pumpkin everything.
Do you ever have pumpkin on pasta?
No.
Pumpkin on pasta is really good. Like pumpkin pie filling with like sausages and onions and on top of pasta is really good. No, I don't know what it is, but it's awfully good. My kids in like the cafeteria or something. I was like, really? What's that? Then we tried it. We got like downloaded a recipe or someplace. Awesome. Seriously, pumpkin on pasta is a great combination.
Do you ever like Do you ever like roast pumpkin seeds and like salt them and eat them?
I am obsessed with eating seeds. I don't know what's wrong with me, but eating pumpkin seeds, squash seeds, cantaloupe seeds. Yeah, that's so good.
It's like sandwich peas also for sunflower seeds.
Sierra, this is our day so far. It's pretty much been a recovery day. All right. Okay, so here's the deal. So far, you guys, Haley didn't quite get the assignment done.
Two questions. That was it.
Two questions.
I did all the rest of it.
Okay.
Why aren't you doing it?
Maybe you can do it. Here's the deal. We're not learning. It's not that much new today.
Okay.
Despite the fact I think we're covering 2 sections in the book. Just like in chapter 2, there was like a 2-section day that was like adding matrices and then multiplying them, and why was this divided up into 2 things? Today it feels the same way. We're learning like one little thing, and yet somehow it takes 2 days. So we're not going to do that. We're going to get all this one little thing. So what we were doing last time was finding feasible regions. An area on the graph that based on inequalities, like satisfied a bunch of these inequalities, right? And on some of the problems, they were just numbers. Like, x is greater than 0, and x plus y is less than 3. Heck, let's do something like that. I'm going to go over here to Desmos. And all those problems were something like y is greater than or equal to x. And x is greater than or equal to 0. And y is less than or equal to 3. And these were just problems with numbers in it. But we knew that y had to be greater than x, so it was this pink region. And x had to be less than 0. Let's make it the other way around. It would make more sense. Let's make x greater than 0. And y had to be less than 3. And the only area that was all 3 of them was this little triangle, the so-called feasible region. It matched all 3. Any place in that region, like, I don't know, 1/2, 2, matches all 3 of those equations. It meets all those constraints. It is that y is greater than x. It is that x is positive, and it is that x is less than 3. This could have been more like the story problems that Miss Haley didn't do. No. For example, let's say that we can make items. How about pumpkin pies? We can make so many pies, P, and so many pumpkin bars, B. Okay? And we have enough pumpkin, we have enough pans, that we could make a total of 10 things. So like pumpkins plus pumpkin pies plus pumpkin bars, it has to be less than or equal to 10. Okay? We only have 10 pans. Whether we put pumpkin bars in them, I know you know you get different pans, but don't even get me started. Alright. So we could use that and make a story problem with this. I don't actually know, does it let me use letters other than X's and Y's? The bars, well, you can only make a positive number of pumpkin bars, right? Oh, there's no B. What does this here say? Oh, apparently it doesn't like it. Alright, we'll have to be less flexible than that. I bet there is a way in Desmos to change it from X and Y to P and B, but we'll call pumpkin bars X, pies rather, X, and the number of bars we make Y. So, we can only make a positive number of pumpkin pies. So, X has to be greater than or equal to 0. Only those numbers work. You can't make a negative number of pies. We can't make 13 bars and negative 3 pies. Right? Even though that would still add up to 10 things. Doesn't work that way. In the same way, we can't make a negative number of pumpkin bars. So right off the bat, we can see that the feasible region so far is this first quadrant. Right? Only positive, the right word actually would be not negative, 0 counts too. We might make 0 bars. Okay. Will work. Plus, we know that the total number, X plus Y, has to be less than or equal to 10. So in this case, we have a feasible region that looks like this little triangle here. That is the graph. Any place inside that feasible region, like 2, 2, might be a perfectly good solution. We could make 2 pumpkin pies and 2 pumpkin bars. I should have used pumpkin rolls, because those are easier. Alright. So any of those places in there is a valid solution. But you know what? Most of the time we want to know is what's the best one. For example, what if we're selling them? What if we're selling the pumpkin pie and pumpkin bars? And Haley, why are you making all these pumpkin pies anyway?
Because I bought everything pumpkin. I have to make.
I am so impressed by this. I love pumpkin stuff. All right, so let's say she's going to have a pumpkin pie stand out by the road. Okay, pumpkin pies by Haley and stuff like that, and she's going to have a road stand. And she's going to make $10 for every pie she sells, or $5 for every pan of bars she makes. So Z will be the dollar she makes. Okay? Most of the time, the problems are going to be more complicated than this. But let's just take that. She might make 2 pumpkin pies and 2 pumpkin bars. She might make 10 pumpkin pies and no pumpkin bars. She might make 0 pumpkin pies and 10 pumpkin bars. The question is, which one will she make the most? Right? Any combination inside the feasible region works. Now, your book proceeds to explain in a very lengthy and awkward way something important is about to happen. The answer as to which will be the right of all the places inside the feasible region, which will be the right answer as to which one makes the most money, and for that matter, which one makes the least, is going to be a special place. But before we get to that special place, I need a term. This function, which is not on the graph. We did not graph any place on here. 10x plus 5y equals z. But that's kind of the function that's keeping score. Right? That is the function that we are trying to maximize, or I suppose minimize. I mean, if that was instead like the cost or something, we were trying to minimize the cost. It's called the objective function. There's always going to be some kind of objective function in these kind of problems. Identifying the objection function can even be something that might be on, say, an exit ticket. So in this case, we have various pieces of information. You can only make a positive number of pies. You can only make a positive number of pumpkin bars. And the total number you can make has got to be less than or equal to 10. Then you know, hey, I want to maximize the amount of money I make. And I make 10 bucks on this, and I make 5 bucks on this. This is the objective function. The best place, the place where you maximize the objective function, and for that matter, the place where you minimize it, get ready to have your mind blown, will always be at one of the corners of your objective region. These so-called corner points. It will either be, I'm totally going to write on the screen. So if I do that, I'm going to, oh, I forgot I had matrices behind here. For just a second here, so that I don't accidentally write on the screen itself, it will have to be, well, okay. Can we make this fit any better? Otherwise I'm going to write on the wall. All of which are mistakes I've made.
There we go.
Alright, will have to either be, it is either at 0, 0, 10, 0, or 0, 10. Now, in this case, the objective region only has 3 corner points. And your path of least resistance will be to just plug these 3 in. 0, 0. If you get 10 times 0 plus 5 times 0 equals 0, one possibility is you'll make $0. Or 10 comma 0. 10 times 10 is 100 plus 5 times 0 is 0 is 100. Over here you'll make $100. And up this one, 0 times 10 plus 5 times 10 equals 50. Make $50. So, your best bet is to go here and make 10 pumpkin pies and no pumpkin bars. Which, in this very simple case, you would have guessed already, right? In this very simple case. Because you already knew, if I'm making so much more money on the pumpkin pies than I am on the bars, why don't I just make all pumpkin pies? Okay? But they aren't always so obvious. Let's do another one, and this time let's just, let's not make it a story problem, just because I don't want to like build a big narrative around it. But let's just say, yes?
Can I help my mom real quick?
Yeah. Yeah, of course.
Like an emergency.
Okay, well good. I'm not good that you have an emergency. I'm glad that you're taking care of it. Okay. All right. So, for example, let's just make another problem. How about we say that our constraints are x plus y has to be less than or equal to 3. Let's just say x has to be a positive number. Let's say y has to be greater than or equal to 1. Here, let me put those on the board first so that we can... I want to make a slightly more complicated shape than a triangle this time. Let's see here. X plus y has to be less than or equal to 3. Nope, let's make it 30. I want more area to work with. Let's make x positive. X is greater than or equal to 0. Alright, y had to be greater than or equal to 1. Alright, and I don't like how dark it is, but whatever. And let's say another constraint is y has to be less than or equal to x plus 10. Let me put that here. Y has to be less than or equal to x plus 10. Okay, this is just some constraints. Let's see, there was y is greater than or equal to 1. Okay, these might be just given to you as numbers in a problem. You know, some of the ones in the book are just math, they're just numbers. And some of them, maybe there was some story problem, but those are our numbers. And then there's some objective function we need to maximize. Let's say z equals 5x plus 6y. And we want to find the maximum value of x. So again, maybe x is the number of cars we sell and y is the number of trucks we sell. And we're going to make $5,000 off every truck, but $5,000 off every car, but $6,000 off of every truck. What's the right number? What's the best number of cars and trucks to sell? All we got to do is get ourselves a list of these points. Here's 0, 1. Here is 0, 10. This one appears to be 10, 20. And this one appears to be, I think it would be 29, 1, but I'm not sure. Yeah. Alright, so using those coordinates, using that graph of the feasible region, remember this polygon here is the feasible region, all you got to do is plug in those points, into your equation, put xy into this, put xy into this, put xy into this, and one of these will be the biggest. Melina, doesn't that sound like a miracle? That it's one of the corners?
It's a Halloween miracle.
It's a Halloween miracle because of the pumpkin?
Yes.
Yes, it's a pumpkin pie spice latte miracle. It's the Great Pumpkin Charlie Brown miracle. It only works for one reason. That's a bit of a cop-out in this book. It only works because these equations over here in the objective function are really simple. It's just something times x plus something times y. Some of them might even have something x, something y, something, like a constant over here or something, okay? But realistically, they're really simple, the right word being linear. Right? There's just x's and y's, right? It isn't something x squared plus the sine of y divided by, it's not rational functions, it doesn't have trig in it, okay? In science, if the objective function here was the strength of the magnetic field near this Tesla coil, this wouldn't work. We're like the strength of the magnetic field was sine of x over y divided by x squared or something. This wouldn't work. But here's the deal. In day-to-day life like business, the money you make off of cupcakes doesn't have anything to do with the sign of the number of cupcakes you made, right? It's just like you made this much profit off each cupcake. So if you sold 10 cupcakes, you make this much profit. If you bake 11 cupcakes, you sell this much profit. Pumpkin pies, right? So fortunately, in like business, insurance, grades, I can't even think what all kinds of examples you do in the class in there. They're always going to be these simple linear functions, and then this technique works. Here's the really, I'm going to use the word badass thing about this. Everything we're doing so far in this class with this kind of stuff, we could make a little graph. Hey, before I do that, there's a word for this whole technique. Names help. This whole technique of figuring out what the feasible region is and then evaluating an objective function at each of the corners is called linear programming. And here's the deal. The linear programming that we have done so far has all just been with two variables. You made, on Desmos, a simple little graph of x and y. Well, it wasn't that simple until you did the homework. But you made a graph, you found your feasible region, and then at each of the corners, you did this. But here's the deal. The same trick is going to work even if not just x and y, you got x and y and z. A three-dimensional graph of inequalities, where instead of it being a line and it colors over here, it's a plane in 3 dimensions, and like this whole volume over here is the feasible region. And even though it's a volume, a weird-shaped polyhedron, if you could just find all those corners of the polyhedron and plug it into your objective function, it would work. X, Y, Z, that would be a three-dimensional polyhedron. There ain't no damn reason why this technique won't also work if you've got 10 variables. And you have a 10-dimensional graph. Andrew, how well do you like drawing a 10-dimensional graph?
Oh, I love it.
Oh yeah, 10-dimensional, it takes you out of the plane of existence, right? But there's no reason why it wouldn't work. If we had brains that could draw a 10-dimensional graph and have a 10-dimensional polyhedron of all these, one of the corners would be the right answer. And there's no reason why it wouldn't be that you could have this many cupcakes, plus this many cookies, plus this many pies, plus this many bars, plus this many cakes, plus this many strudels, plus this many hoskas, plus this many fruitcakes equals 100. I mean, you suddenly have a 9-dimensional problem. And guess what? In real life, they have to do this. Right? Donut Bank has to know how many glazed, frosted, iced, fondant to make. Right?
Well, sometimes you gotta get out of here going to 3-dimensional thinking and see.
So, here's the deal. All the problems we're doing so far are just going to be this, where we're making a happy little graph in Desmos, and our happy little graph in Desmos will have corners, and we will evaluate the function at this. But we're going to be, in the next chapter, getting more complicated than this. We won't be able to have a graph where we can just look and see where the corners are. We're going to need techniques that will help us do this. That would have worked just as well with these two-dimensional pictures, but instead we're going to be doing it this way so we have an idea of what it is we're trying to do. This linear programming with just 2 dimensions. So that when we have more complicated problems and we're using the matrix tableau techniques and so on, we can picture what we're doing even though we can't make a graph of it anymore.
Are you going to upload that video?
Yeah.
Okay, so my mom's been texting me.
Yeah, I recognize you're distracted, Luke's down here, and Sierra's down here. So, I mean, we got to kind of do what we got to do.
Okay, I'm sorry.
All right, no problem. No. So here's the deal. Somehow or other, your textbook took like 2 whole days to do this. Which is odd, considering it wasn't really that much material. Like somehow or other we managed to do it in like 20 minutes. So, here's what's going on. If you look at pages 124 to 126, and I just realized this is less ideal. There you go. There's just a handful of problems. And these little problems here are, if I remember right, the ones in this first section, they're just numbers. X plus this equals less than y. And then 3x plus y is less than 5. And they're just x's and y's. And then the second part, which is actually section 3.3, I believe, it starts on page 133. I only gave you 3 problems, but they're problems. Bob sells grain. He can only store 1,000 bushels of grain, whether it's corn or beans. He makes $5 a bushel on corn and $2 a bushel on beans. He must have at least 3 times as many beans as corn on stock. What's the optimal amount of corn and beans he needs? Okay, real problems. Do you think the guy in the grain elevator is actually doing linear programming? Like this? He might. He probably went to, like, agribusiness school.
Might not be.
He might. More than likely, what actually happens is there's software that's helping him make that decision, right? There's probably software that his grain elevator uses to tell him what's the optimal amount to buy. Because there's probably more than just 2 considerations, right? Probably also things like changing market prices and things like that have to be figured in too. So in real life, but I mean, that really big choices as to like how much insurance to sell or how many donuts to make a donut bank. There almost certainly is some app or some program at Donut Bank that's making a decision each day at how many. Odds are nobody's sitting there doing the math and doing this, right? But on the other hand, the business software that runs the place is probably making a decision. Okay? My wife's dental practice. They do dentistry. That's just, people come in and whatever you need. But part of it too is, they sell like electric toothbrushes, and they sell, like when you go, because after you've been scraped for an hour, you're kind of in the mood to buy an electric toothbrush, right? So you're like, I don't want to deal with that again, right? So there's electric toothbrushes and there's other things in there. And the company that provides, that actually sells it through her or whatever, has a website that they know things like how much space she has to store them, and how many there's only this many feet, and each one takes up this much space, and they know they sell this many of this, and they know exactly the right number of them to have on stock. I doubt someone's sitting there doing the linear programming, but that's in fact what the software is doing. Is figuring out what's the best number of those things to have in stock, so that they can make the most money by people's gums hurting after they were cleaned. All right. Yes, Malia.
The assignment, is it just like on paper, or do you want us to like send us?
If I remember right, all of these problems involve making a graph.
Okay, so send
And so if you have, let's make that the rule. If your problem involves a graph, send me the graph. Okay? Let's just make that our new rule.
Can we just put it in like a Google Doc?
Yes, that's what I want you to do.
Okay.
Just go ahead, do a screenshot. I love those screenshots of them because I see the equations you used. Okay? It's very easy for me to figure out if you're doing the right thing. And so, whereas like you draw us a sketch on a piece of notebook paper, I don't know what the hell you're doing. Okay? So, and then yeah, just paste it into a Google Doc and share it with me. That's perfect. Okay? Andrew, did you have a question?
Yeah, about a few of them.
Okay. Let me real quick get the exit ticket up, and then we will, that way you can do it, and it should just take a minute, and then we'll do what you got a question about. All right.
Hey, do you want to know what the etymology of the day is?
Sure.
It's the word etymology. It comes from the Greek etymon, which is true sense, original meaning, and logia, which is study of, a speaking of, and then smacked together, the original Greek etymologia was analysis of a word to find its true origin, or study of the true sense of a word.
Interesting. Interesting. All right, so you got that. Do you listen to Words, not Words Between Friends, what is it? Away with Words?
No.
It's a great podcast about etymology. All right, Andrew had a question. What you got, Andrew?
I was going to ask, does minimize subject and maximize subject just mean graph it and then do?
Yep. It means those are the so minimize subject to means that those are the constraints. Those are the inequalities that we are making our feasible region from.
Okay.
And then the function that you're saying maximize, that's your objective function.
So is it, I just want us to graph it then?
Yeah, let me see which we got going on there. So which one are we talking? Number 7. So number 7, it says minimize z equals whatever. So that is your objective function. Z equals whatever, that is the function that you are trying to find out. Where is it? Minimize, you're finding the corner of your feasible region at which that function is smallest. Okay? And these are your 4 constraints. So I would just take these guys right here, make yourself a bounded, make yourself a graph. Notice, by the way, if you look at the examples, like number 16 on page 125, it's not bounded. The answer will never be out in the unbounded area. Okay? Part of the way these problems work, it will never turn out that way. If your objective region is, like, I'm telling you, your what's the right word? Your feasible region looks something like, like this, and if this whole thing is feasible, you actually don't need to worry about it. It will still just be one of these corners. Even if it's unbounded. Alright, I'm going to turn the camera off for Sierra.